In this video, we solve problem 12.4.027 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the tangential and normal components of acceleration at the given value of t for the plane curve generated by the vector valued function r of t. R of t is e to the t times I hat plus e to the negative 4t times j hat. I prefer to write that in component form, like this. We're interested in the tangential and normal components of acceleration at this particular time t equals 0. Before we do the computation, I just want to remind you of what those values are. So if r of t represents the position function, if we take its derivative, we get r prime, that's the velocity function. If we take the derivative again, we get the acceleration function. Now it turns out that our acceleration vector can always be written in the following way. The acceleration is a constant times t hat plus a constant times n hat, where t hat is called the unit tangent vector. That's the unit vector in the direction of motion, or the direction that we're moving along this curve if r of t represents our position function. And n hat is called the unit normal vector. That's the direction that we're turning if we're moving along this curve, if we happen to be turning, and if we happen to be moving. All of this would be true. So this a sub t and a sub n, these are just scalar values. This a sub t is called the tangential component of acceleration, and a sub n is called the normal component of acceleration. Now, if a sub t is positive, what that means for us is that the acceleration has a component that is in the same direction as t hat. So that means that we are speeding up. We're going faster and faster in the direction of motion, so we're speeding up. Now, if a sub t is positive and a sub n is non-zero, that means we're turning at the same time. So this might be the situation where we're speeding up and we're turning, and our curve in that case might look something like this. Since we're turning this way, our n hat points that way. Since we are moving in this direction, our t hat points that way. And since we're accelerating in that direction, it would look like that. Now, it's also possible that our acceleration vector has a component that's parallel to t hat, but it isn't in the same direction as t hat. It goes in the opposite direction. That's the case when a sub t is negative. In that case, our speed is changing, but since our acceleration is opposing that motion that is going this way, we're actually slowing down. So if we're a sub t is negative, we're slowing down. If a sub n is also non-zero, that means we're turning. So we're turning in this direction and we're slowing down. So the curve might look something like this. And actually, I'm not really sure how I would have to draw the curve to indicate that we're slowing down versus speeding up. But you get the idea. This is the direction that we're going. That is the direction that we're turning. And we've got one of these two possible cases. Of course, not thinking about the special cases when a sub t equals 0 and a sub n equals 0, or a sub n equals 0. But this helps us sort of interpret what these values mean. Now, I can use either one of these triangles to find a formula for a sub t and a formula for a sub n. So let's think about this situation first. If my acceleration vector looks like this, and my t hat is this way, the component of the acceleration vector in the direction of t hat would look like this. Now, the magnitude of that component can be found using right triangle trig. We make my acceleration vector a little bit longer. So this would be a sub t times t hat. This vector is a sub n times n hat. And the magnitude of that component is just a positive number. It's going to be that a sub t. Well, since a sub t is the length of the adjacent side of this triangle relative to this angle theta, it can be given by the magnitude of our acceleration vector, that's the magnitude of the hypotenuse, times the cosine of theta. Now we don't generally know what theta is, but this looks an awful lot like our dot product formula. So if we want to, we could multiply this by the magnitude of t hat, which remember is just 1 because it's a unit vector. Every unit vector has a length of 1. And so that gives us a sub t, is equal to this formula, and that formula is the dot product, or is one way of writing the dot product of the acceleration vector and the unit tangent vector. Now, that same situation holds over here, even though the triangle itself would look a little different. If this is my acceleration vector and this is t hat, the angle between t hat and my acceleration vector is obtuse in that case. But still, if I wanted to find the component of acceleration that is parallel to t hat, so this would be a sub t times t hat. Since a sub t is negative in this case, I'm taking t hat and multiplying by a negative number, so the vector goes in the opposite direction. I would still use the dot product of a and t hat. I would still have a sub t is the cosine of, or the magnitude of my acceleration vector times the cosine of this angle. But in this case, the cosine of the angle would be negative rather than positive. So this is the formula that we use for a sub t. Now it just comes from trigonometry, either right triangle trig or how that right triangle trig extends to quadrant 2, as we see over here. Now the acceleration or the tangential component of acceleration can also be written this way. We don't tend to use this formula though, but it's a good reminder of what the acceleration in the direction of the unit tangent represents, or the tangential component of acceleration represents. This says it's the derivative with respect to time of speed. So if we're not speeding up or slowing down, then the speed would be a constant and we'd get 0 here. But if our speed is increasing, that would mean this is positive, so we're speeding up. If our speed is decreasing, that would mean this value is negative, so we're slowing down. So in practice, even though I don't use this formula in computation, I will tend to use that for interpretation. Now, to find the normal component of acceleration, we could use a dot product as well. We could think about taking our acceleration vector and finding the projection of the acceleration vector onto the unit normal vector, which we could find using a dot product as well. So this formula is true. It's accurate, but the unit normal vector is kind of difficult to find. So rather than using this formula, we might want to use a different formula instead. Now, I notice right here that I've got a right triangle, and we know the Pythagorean theorem holds for a right triangle. This side length squared plus this side length squared equals that side length squared, or a squared plus b squared equals c squared by the Pythagorean theorem. We've got a similar right triangle over here. A squared plus b squared equals c squared. In both cases, we're taking a sub t and we're squaring it. And we add that to a sub n squared. And that equals the magnitude of the hypotenuse squared, which is the magnitude of our acceleration vector. So just by the Pythagorean theorem, we get this equation. It's easy to find the acceleration, and we've already got a formula for a sub t. So with the acceleration vector and a sub t, we can solve this, or the only unknown in this equation, excuse me, is a sub n. So if I want to solve for a sub n, I just subtract this from both sides and take the square root. A sub n is always positive. Well, actually, it's non-negative. It's either positive or 0. And we get this. So rather than using this formula, I recommend that we use this other formula that comes from the Pythagorean theorem. So let's use this one instead. Now there is another formula for a sub n. Turns out that the normal component of acceleration is given by the curvature times the speed squared. But again, we don't tend to use this formula because finding curvature takes a bit of time. Finding the speed isn't that difficult, but finding curvature would take some time. So we'd have to take the curve, find the curvature, find the speed, square it, multiply, and all of that. That is more involved than just using this formula. So just using a little bit of trig, we're able to find formulas that will work to give us a sub t and a sub n. And we could use these formulas as well. We choose not to, but instead we use these formulas to interpret a sub t and a sub n. This formula reminds us that a sub t is a measure of the rate of change of speed. So it tells us whether our particle is speeding up or slowing down at a particular t value as we move along the curve. Now this is related to curvature. It tells us whether we're speeding up. If this is non-zero, or excuse me, not speeding up, it tells us whether we're turning. If this is non-zero, that means we are turning. And the value of this is proportional to the curvature. So if we're turning a lot, if it's a sharp curve, that curvature is large. Or if we're speeding, if we're going pretty fast, then that constant a sub n, the normal component of acceleration, turns out to be proportional to that speed squared. So if we doubled the speed, we would multiply our normal component of acceleration by a factor of 4. Okay, so those are the formulas that we'll use. Now let's use them. Now, one other thing I would mention, or I want to mention before we move on, is that we can use these for functions of t in general. So we can find the acceleration vector in general, the unit tangent vector in general, take the dot product and find the tangential component of acceleration as a function of t, and then substitute in t equals 0. But it's much easier if we find this vector and this vector at 0 and then take the dot product. And then once we have the acceleration vector at 0, we can find its magnitude at 0. And we can use the tangential component of acceleration at 0 and substitute that here to find the normal component of acceleration at 0. It just makes it a little bit easier so that we're not working with functions of t that look relatively complicated. Instead, we'll just be working with a couple of vectors with components that are just numbers. They're just numerical values that we'll be able to look at and we'll know after we substitute in t equals 0. Okay, so that's the plan. That first we need to find the acceleration vector and the unit tangent vector, and then we'll take our dot product. We'll start by taking the derivative of the position function to find the velocity function. The derivative of e to the t, it's nice and easy, it's just e to the t. The derivative of e to the negative 4t requires us to use the chain rule. So we say the derivative of the outside function is the derivative of an exponential. Derivative of an exponential is e to that power. And then we multiply by the derivative of the inside. The derivative of negative 4 times t is just negative 4. That's velocity. We want acceleration, so we're going to do that again. Derivative of e to the t is e to the t. And when we take the derivative of this guy again, we just multiply by another negative 4. Negative 4 times negative 4 is positive 16. Okay, now we could use this function to t, but again, it'll be easier if we evaluate this at time t equals 0 first. So let's evaluate this at 0. The computation will be easier. So we'll just have e to the 0 as our first component and 16 times e to the 0 as our second component. E to the 0 is just 1. So the acceleration vector has components 1 and 16. Now for the unit tangent vector, remember that's the tangent vector that is exactly 1 unit long. Now our velocity vector is the wrong length, but if we take the velocity vector that always points in the direction of motion. If we divide by its magnitude, we get the unit tangent vector. So what I would recommend from here is that you compute the magnitude of r prime just by taking the components, squaring them and adding them and taking the square root. So I have an e to the t there and a -4 e to the -4t there. When you square this, you multiply the exponents, square the -4 to get the 16. Here you've got e to a power raised to a power, multiply the exponents as well. And that is our magnitude. So if I take this vector and I divide by the magnitude, I get t hat in general, but what I want is t hat at 0. So I can evaluate this at 0 and this at 0 and then divide, and that'll give me t hat at 0. So first we'll compute r prime at 0. E to the 0 is 1. So this is just a vector with components 1 and -4. And then we can evaluate this at 0. It's actually probably easier to just compute the magnitude of, again, with this particular vector. Just take the components, square them and add them and take the square root. And so we get the square root of 17 there. So our unit tangent vector at 0 is r prime at 0 divided by its magnitude at 0. And that's just this guy, the vector with components 1 and -4 divided by the square root of 17. So you just take each of the components and divide by the square root of 17 and you get this. Okay. So now that we've got the acceleration vector and the unit tangent, we're going to take their dot product to find a sub t. At time t equals 0. And the acceleration vector at time t equals 0 had components 1 and 16, and then this was our unit tangent. Remember how dot products work? You're going to multiply component by component and add. So you'll have 1 times this, which is of course that 1 over square root of 17, plus this times this. It's going to give us a -64 over square root of 17. And of course we can add the numerators, keep the common denominator. We get -63 over the square root of 17 as the tangential component of acceleration. Since it's negative, that just means we're slowing down. Before we go on, let's talk about what we just did. We found the first and second derivative to find the acceleration vector, and then we evaluated the acceleration vector at time t equals 0. So compute r prime and r double prime, and then we evaluate. Then we evaluated r prime at t equals 0. Find its magnitude right here. And then we just take this vector and this magnitude and we divide to find t hat. And then from there, you've got your t hat at 0 and your a at 0. You take the dot product. So we compute that. All right, so that was the first part that we were asked to find. The second part that we were asked to find was that normal component of acceleration. So we're going to use this formula. We're just going to evaluate everything at t equals 0. Easy breezy. So our normal at 0, our normal component of acceleration at 0 is this. Okay. And we've got everything that we need. We just need to compute this magnitude. So I'll take my acceleration vector at 0, which we found earlier. It had components 1 and 16. And we want that magnitude, the magnitude of that vector, but we want it squared. So the magnitude of the acceleration at 0 would be the square root of 1 squared plus 16 squared. But then I want it squared, so I will square both sides. That'll just get rid of the square root. And we'll just have 1 plus 16 squared, which is 257. Okay. And then we want to substitute a sub t at 0. We've already computed that. That was that negative square root, or a negative 63 over the square root of 17. If we square that, we get this. 63 squared turns out to be 3,969. And in the denominator, we've got a 17. So we'll just substitute these two values into that formula there. At 257 minus this. And then we'll take the square root. And we get 20 times the square root of 17 over the square root of 17, or over 17, excuse me, if we rationalize. Or if we had chosen not to rationalize, we would have this. So either one is fine. They're both the same number. My calculator gave me the rationalized version. And that's that. Since that is non-zero, that just means we're turning. We're slowing down the direction of motion and we're turning. And these are the coefficients of t hat and n hat in our formula for A. So even though we're not asked, we could write our acceleration vector this way. Our acceleration vector is a sub t times t hat plus a sub n times n hat. And a sub t turned out to be negative 63 over the square root of 17. And a sub n turned out to be 20 over the square root of 17. If we take those two vectors and we add them together, we get our acceleration vector.